All right, so 2.7, we were just taking the derivative implicitly, and a lot of the times when you take the derivative implicitly, you end up with a quotient as your derivative. And very often it's in terms of two variables, but it could be in terms of one. But we most of the time end up with a quotient. So one of the things that you're going to be asked to do then is to find where you have vertical tangents, horizontal tangents, and it's going to come down to different parts of that quotient equaling 0. So let's just kind of review this. I think we kind of know this, but it's worth mentioning again. Whenever you have a derivative that's a quotient, you're going to obtain a horizontal tangent line when the derivative is equal to 0, right? Anytime a derivative is 0, you're going to have a horizontal tangent line, right? But in a quotient is equal to 0 when the what's 0? The numerator, right? Not denominator. The numerator. Good. As long as the denominator is not 0. So any 0 over non-0 in a quotient is going to give you 0, and you're going to have a horizontal tangent. If you're asked to find a vertical tangent, that's going to be when the derivative is undefined. And in a quotient, we're looking for a particular type of undefined because we want it to be a vertical tangent. We want it to be infinity, right? So how do you get infinity or a vertical asymptote? When it is non-0 over 0. So essentially when the denominator is 0 and the numerator is not. Now, the tangent line is going to be undefined. It's not a vertical tangent line. It's undefined for a different reason when you get 0 over 0. So if you're ever in the process of working with a problem like this and you have a value of x that makes the numerator and denominator 0, no tangent line exists, you're going to throw these points out, okay? So really what we're interested in is horizontal tangent, setting the numerator equal to 0 of the derivative, and then vertical tangent, setting the denominator equal to 0. You ready to try it? Example 7. The graph of the equation x squared plus y squared is a what? Do you recognize that without me telling you? You could solve for y by taking the square root. This would be like the end of algebra 2, conic sections. Yeah, it's a circle centered at the origin with a radius of 2. Right. So in general, not that you need to necessarily know this now, but x minus h squared plus y minus k squared equals r squared. That's a circle with the center at h comma k and a radius of r. So in this case, our h and k are 0. Part A, it says sketch the graph of the equation. Okay, we could do that. We need a y-axis, we need an x-axis. And if the radius is 2, you can just go out to 2 over here, up 2 over here, out 2 over here to negative 2, and down negative 2 here. And then with your best circle drawing skills, you can do something like that. Not bad. That's good enough. I think Notability actually draws circles for you if you want to explore that. Okay, sweet. Now, we kind of already know a lot about this circle in terms of rates of change, right? Do I know where this graph has a horizontal tangent line? Yeah, 0, 2, and 0, negative 2, right? Horizontal tangent lines right there. 0, 2, 0, negative 2. So if this were a calculus multiple choice question and you were asked to find the coordinates of the horizontal tangent lines, would you need to use calculus? No, okay? As long as you understand what the calculus question is asking, you can get it by another method. What about vertical tangents? Do we know where they live? Do they live at all? Yeah, what order pairs? Negative 2, 0, and 2, 0. Okay. So what we're going to do in this problem is essentially verify those results using calculus, because if the graph knows where the horizontal and vertical tangent lines are, and we know where they are based upon the graph, shouldn't the calculus know as well? You would hope so, right? Because calculus would be the older, wiser, bigger brother of algebra 2, right? All right, let's see. Part B says to find dy dx. Well, I noticed that my equation x squared plus y squared equals 4 is not solved for y. So then I asked myself, can I solve it for y? And I think I can. I think I can. I remember that story from first grade. Yeah, I could do that. I can huff, and I can puff, and I can blow your house down. That's a different story. What do we do to solve for y? We got to take the square root. And anytime we take the square root of something, we have to remember to not forget to do what? Plus or minus. Okay. Now, I did solve for y, but I did not solve it for a single explicit equation. I have to work with two equations. Now, working with two equations wouldn't be bad because at least they're explicitly solved for y in terms of x, but I'm going to have to know when to use which equation and when to use the other equation. That might be a burden that I don't want. The positive root one is going to be this one here. And of course, if you have a negative out front, that just reflects it across the x-axis. I don't think I want to work with two equations. Do y'all? Especially when I know that there's a method for not having to work with two equations, right? Let's just take the derivative how? Implicitly. Good. So let's do it implicitly. To do that, we're going to have d dx of the left side and the derivative with respect to x of the right side. And make sure, again, that it's d dx, not dy dx, and it must go in front of each of the expressions. Go ahead and rattle that off while I invite our guest in. Andrea, yeah, come on in. Oh, okay. Just come on in and just sit right here in the back, and then lunch is going to happen pretty soon. Okay? Huh? Yeah. Okay, x squared becomes 2x dx dx, right? Do we need dx dx? No. Plus the root of y squared is 2y dy dx. Do we need dy dx? Yes, we do. And of course, the derivative of 4 is 0. All right. So what I'm going to do now is solve for dy dx, and I think I could do it in one step here. Bring the 2x across, it becomes minus 2x. And then I'll divide through by the coefficient of dy dx, and I get 2y. And I know that I can divide that out. Ready? And I get negative x over y. So what that's going to do, it's going to give me the slope of the graph of the circle at any point I want. As long as I know the x and the y, I can plug it in. So part B, it says using calculus, now verify that the graph has the horizontal tangents at the points that we already discovered. Okay? So how are we going to do that? What do we know? What are we going to do? A graph will have a horizontal tangent line when it's what is what? When the what is the quotient of the what? The derivative, right? It's important to say that. So this right here, believe it or not, on a free response, you already earned a check just by saying dy dx equals 0. If you know it's a quotient and you want to say 0 over non-zero, guess what? Same check. At any rate, it comes down now at this point to setting the numerator equals 0. I'm going to associate the negative in the numerator with the x. Are you all okay with that? I don't like it floating out front. So now that I have that, and I've earned the check, I'm going to go ahead and set my negative x equal to 0. And all I got to do is solve for x. And that's pretty easy. I get x equals 0. Yay! Now, how do I find the accompanying y values when x is 0? What's that? Do I have an equation that relates x to y? Yeah, right there. So all we have to do now is plug our x value back into the original equation that relates x to y and find the y values that go along with it. So whenever you're doing multiple parts on one problem, it's good to kind of put like stage notes, like narrate your way through there. So I'm going to say when x equals nada. And we'll plug it in. 0 squared plus y squared equals 4. Oh, German. Wenn x equals ganz nichts, haben wir ein y squared equals 4. Fear not, though, because we know how to do this. We take the square root of both sides and we get plus or minus 2. And now that we have plus or minus 2, we're going to answer the question. We wanted the points. So the points are going to be the point 0, 2 and 0, negative 2. Okay? Yes, sir. Yes, sir. How do you determine if dy over dx is 0? Well, we wanted to find the horizontal tangents, right? And we know the... Just like putting it there to determine. Yes. Yes. If I know I want the horizontal tangent lines, I know the slope needs to be 0. I know that's the derivative that's 0. Because it's a quotient, I know when it's the numerator 0. Now, did I just verify it? Did we get the same points? Indeed, right? Yeah. All right, so using calculus, verify that where the vertical tangents are. What are we going to show to get that setup point? dy dx equals Yeah, you could say non-zero over 0. That'd be great. And then after you say that, you've earned that point there, then it's about setting the denominator equal to 0, right? So you set the denominator equal to 0, and then you solve. Ta-da, right? It's solved. How do we find the x values now that go with it? Same idea. When y equals 0, we get x squared plus 0 squared equals 4, x squared equals 4, and x equals plus or minus 2. And so the points are going to be 2, 0, and negative 2, 0. So why did we do the calculus even though we already knew the answer? To prove that the calculus works, right? Because you think we're always going to be able to recognize what the graph looks like when it's implicit? Heck no. But now we have a method that we can trust and do reliably and faithfully to get the right answer. Now here's a nice follow-up question. At what value or values? Ooh, that kind of hints that there might be more than one, right? Foreshadowing. At what values of x is the slope of the graph 3/4? Well, let's see. We'll come into the graph here. 3/4. That's going to be, like if I draw this 45-degree line right here, positive 3/4 is going to be, a little bit less steep. So maybe it's going to be right there. And then maybe it's going to be about right there. And because of the symmetry of the circle, these two ordered pairs should be what's of each other? Or like origin symmetric? Yeah. So it should have the same magnitude on the x and y. So I guess it's time just to start guessing, right? Sure. We have the derivative. If I can figure out values of x that when I plug it in are going to give me positive 3/4, I think I could do it, right? So how about negative 3 and positive 4? Will that work? I mean, when x is equal to negative 3 and y is equal to positive 4, and I plug it in, I get 3/4. What? Oh my goodness. Oh, that's good. Oh yeah. That's going to be outside the circle. That doesn't quite work. Now, you could use proportions because you notice that if you have circles with different sizes or diameter radius, all of those points that are proportional are going to land on that same line. Any ideas how we can do it then? Because I tried and I landed outside the circle. That means I missed the mark. I want to know where the slope is 3/4. Set it equal to. Yeah, we have an equation that gives us the slope at any point. So let's go ahead and set the derivative equal to the slope we desire, just like we did above, right? We set it equal to 0 and d and e. You're going to get a check right there just for that. That's called your setup. Now, it'd probably be better to set the actual expression that is dy dx equal to 3/4 so that we can solve. Speaking of solving, I have one equation with two unknowns. Is that good? How's that going to help me? Well, good question. No, we never give up. You know what we could do? We could solve it for one of the two variables, can't we? And then plug it in. It's like a system of equations. Here's one relation between x and y that we want to force to happen. We have another relation between x and y that we know has to be true also as well, right? The x squared plus y squared. This is a very, very typical thing that's going to happen when we have equations that are obtained implicitly. You're not going to have one equation with one unknown. You're going to have something like this. And all you have to do is solve for one of the variables. I'm going to multiply both sides by negative y. Negative y. Why? So that we can get x equals negative 3/4 y. Now here's a relation between x and y, and we want to see where this is true. So now what I can do is I can plug this in to my original equation. Plug in to original. And that's going to have to wait till after lunch. So go refuel when you come back. We got a lot to do. And I guarantee it's going to be just as fun as we've been having. Maybe even more so.